I'm going to start recording and I'll have the chat open. So you guys can always unmute yourselves or type in the chat. For the first one here, we have the expression, the correct KSP expression for the dissolution of Ag2CrO4. So what do you guys think for this one? Let me cover my answer key. Were there any that you like immediately ruled out?
So I guess I just thought about it as like I had to write out the equation, and then I kind of just, I'm not even gonna lie, I picked D just because I guess because of the Ag2, like the 2 is there. So it just made sense.
Yeah, and that's the answer. So we can write out the expression for look at the solutions of the Ag2CrO4, and this is a solid. And then it goes to aqueous. So it would be 2Ag plus CrO4, 2 negative. So and these are both aqueous. So the reason that it's not this one is because well, for 2 reasons. 1, because it doesn't square silver, but 2, because Ag2CrO4 is a solid. So if you remember, only aqueous and gases get put into your K expressions. So you can immediately rule out this one for that reason. And then, just like Bryce said, you need the coefficient of 2 in front of the silver. And so that becomes when you square it in the KSP expression. So there's other ones like this one doesn't have Ag squared or CrO4 squared. So that wouldn't be it because Ag plus isn't squared. And then for this one, CrO4 2 negative is squared, and that one doesn't have any coefficient in front of it. So, or it has a coefficient of 1 in front of it, so it wouldn't be squared. So just like Bryce said, it would be this one, the KSP of Ag plus squared times CrO4 2 negative. Do you guys have any questions about any of that?
No.
Okay, sounds good. Okay, so for this next one, oh, sorry, go ahead.
Oh, no, I was saying, yeah, I'm good.
Okay, so for this next one, we have to do this molar solubility of MgOH2 in pure water. And so we'll need the KSP to even, with the KSP expression to even start, start solving this one. So we can write the solution expression like just like how we did for the last one. So we have MgOH2, and then it's going to dissolve to, so it would be solid, and then it would be Mg2 plus, and then plus 2OH negative. And then these are both aqueous. And so the KSP expression, do you guys have any idea what the KSP expression would be?
Wait, no, never mind. Wait, so 4SQ?
Yeah, so exactly, because it would be,
okay.
Yeah, it would be Mg2 plus times OH minus squared, and then because you'd have like the 1s from here and the 2s from here, and the 2s gets squared, it ends up being 4s cubed. And so your S expression is 3.72 times, or your S is equal to 3.72 times 10 to the negative 5th. Do you guys feel like you feel good about that? Do you have any questions about what S stands for, or like what that means, or how you do 4s cubed or solve for S or anything like that? Or was that okay?
I got confused a little bit on this, but it makes sense now.
Okay. Do you understand like the why you do like a 1s here versus a 2s here and everything?
Yeah, because of the coefficients, correct?
Yeah, because like if you did an ice table, it'd be like double the amount of OH getting added to it. Yeah, perfect. Okay, so, and then just in case for the math, you have to divide by 4 first, and then you would take the cubed root. So if you ever have to take the cubed root in your calculator, you can also just like raise it to the 1/3 power, which might be easier sometimes than having to do like the weird like special cases of a of a certain root on your calculator too. So yeah, so for this one, it should be S equals 3.72 times 10 to the negative fifth. And so that's what the molar solubility is. And so it would be this one. Okay, so then for the third one, we have calculate the molar solubility of CaCO3 in pure water. So it's a really similar one to this one. The only thing that's different for this one is that, like obviously CaCO3 is a different compound than what was it here? MgOH2. And this one's actually a little bit like less complicated because CaCO3, it's not like, there's nothing that's a coefficient in front of it. So it only, it's just KSP equals Ca times CO3. And so when you solve for S, you just square root your KSP, which you're given here. And so you should get an S value of 7.05 times 10 to the negative fifth. Do you guys have any questions about that one? Were you all able to get that? Or does it make sense now if you made a mistake or anything?
Makes sense.
Okay. Kelly, are you good with that?
Yeah, that makes sense. I'm good.
So then it's like the exact same thing here now, again, just with another compound. We have Ag2SO3. And so for the equation for Ag2SO3, you'd have 2 silvers, and then you'd have only one of those. I think this is sulfite. And then you would, because you have the coefficient of 2 in front of the silver, in your KSP expression, the silver has to be squared. So it's a little bit different. It's almost like the opposite as your MgOH2, you had like your anion squared. Here you have your cation squared. And then SO3 2 negative is only, it's just raised to the first power. And so for your KSP expression, you'd have to, you do S times 2S squared. So you get a total of 4S cubed. Because you'd square that 2 and then you would square that S and multiply the S's. So in order to solve for your KSP, you'd have to just, I guess this is, it gives you the molar solubility. Sorry, I said this was like the other one. It gives you the molar solubility you're solving for KSP. So you have your KSP equals 4S cubed, and the way we had been doing it before was that we would have our KSP, and so you divide by 4 and cube root it, but now it's the opposite thing, where now you're going to multiply by 4. You're going to take the cubic root and then multiply by 4. So you should get 1.49 times 10 to the negative 14th as your KSP value. And it was kind of like opposite as like when you solve for KSP, but was it still, it was kind of opposite of when you solve for molar solubility now that you're solving for KSP. Did it still make sense, or do you have any questions about how to solve for that?
No. Well, not for me, at least.
Okay.
Yeah, I'm okay.
Okay. And then it's the same kind of a thing for this next equation here, or for the next question here. You're given the molar solubility and you find the KSP. So it's the exact same thing, just with a different expression. And the other one had the cation being squared, but this one has the anion being squared. And so you would have to just do 2S or S times 2S squared, and so you'd have 4S cubed. And so you just plug this in your molar solubility value, and then you cube that, multiply it by 4, and you should get an overall KSP of 4.38 times 10 to the negative 23rd. Any questions about that one?
No.
Okay, so I feel like all those, like up to this point, were kind of just
The
like
same thing.
Yeah, pretty standard. Yeah. And then it gets a little bit harder for this next one, I think. Although I do think, like, if you feel comfortable with this kind of stuff, I think that's good, because I do think that a lot of the questions, like when I look at the textbook, pretty much all of the questions are questions like these first 5. And they're pretty, they kind of like build the foundation. If you know how to do that, you're able to figure out a lot of the other stuff. So if you're feeling good about that stuff, that's pretty good, I think. For this next question, though, it's a bit more difficult, and I think that it's kind of like more difficult at face value, because the actual calculation isn't so hard. It gives you the solubility of copper 1 chloride, and it gives it to you as 3.91 milligrams per 100 milliliters of solution, and you're supposed to calculate the KSP. And so like that might have seemed kind of confusing, because it gives you the solubility in like milligrams per milliliter, but really what you have to just do is just convert this solubility is like, for example, up here, it gives you the molar solubility in terms of molarity. This time it just gave it to you in terms of like grams per milliliters of solution. And you've done a million times when you get something that's in grams over milliliters of solution, you just have to convert it into molarity, which is the exact same thing you have to do here. And so in order to figure out the molar solubility of copper chloride, you just need to first make sure that your units are okay. So first get everything into grams. So you divide by 10 to the third, and then divide by 10 to the third again because you're in milliliters. Or actually it should be the opposite here. It should be 10 to the third milliliters over 1 liter. So make sure that I didn't mess up the calculation. And so it should be 10 to the third over 1 liter. And then you'd have 1 mole of copper chloride over the molar mass of copper chloride. And let me just check to make sure that I didn't mess up the actual calculation. So it would be, these two cancel out, so it would just be 3.91 divided by 100. And then divide that by 0.0. 391. Thank you, sorry. Okay, and then it would be 0.0391 divided by 98.999, and I did mess it up here, so it would actually be 3.95 times 10 to the negative fourth here. And so that was, it's like your molarity now. And so let me just close out of this. It's not. Okay, so now you have you'd have 3.95 times the negative fourth, and then you just have to plug it into your KSP expression because now it's just like your S value. And so you'd have CuCl goes to Cu plus and Cl minus, and because those are 1-to-1 ratio, and they don't have any stoichiometric coefficient in front of them, it would just be S squared, because you just multiply each of these would just be S. And so you'd plug this value in for both of them and square it, and you would get 3.95 times 10 to the negative fourth, and it would be squared. And so it should really be 1.56 times 10 to the negative 7. So I need to correct that on the quiz, so don't worry if you didn't get one of the answer choices here. It should be 1.56 times 10 to the negative 7th, not to the negative 19th. Does that make sense? Do you guys have questions about that or anything?
Yeah, so basically for this question, you're just trying to find, once you find like the molarity, then it's just doing the same thing as like those other questions before this, correct?
Exactly.
Like that same sort of routine. All right.
Exactly, yeah. It's just like, instead of giving you the molarity, the molar solubility in terms of molarity, it gives it to you in terms of like milligrams per solution. So once you convert it, it's the exact same deal as before.
Got it. Okay.
This next one is more of like a theoretical question. So it's which solution is the solubility of MgOH2 the greatest? And so you're given a solution with a pH of 4, pure water. The solubility is going to remain the same in all these solutions, or the solution with a pH of 10. So do you guys remember the common ion effect, what that is?
Yes.
Do you want to explain what it is really quick?
Isn't it like when both compounds have the same element in them? Like they both have like Cl or Na or something like that?
Exactly. And so that's like what we're dealing with right now, right? Because in these solutions that have pHs, or like not even that have pHs, but like in all these solutions, like water has OH minus in it already. And so we have to consider how the OH minus concentration is going to like change with different pHs. And so if you remember at pure water, the OH concentration is at a pH of 10 to the negative 7th. Or sorry, not a pH. The OH concentration at a pH of 7, the OH concentration is at 10 to the negative 7th molarity. Equals 10 to the negative 7th molar. but at a pH of 4, the OH minus concentration is going to be at, it'll be 10 to the negative. So it would be, I think it'd be 10 to the negative 10th that you'd have the molarity. So it would be less OH minus than in water. And then if you had a solution with a pH of 10, you have an OH concentration, an OH minus concentration of 10 to the negative 4th molar. So much more than you had in water. And then, so we can kind of rule out immediately the solubility is the same in all solutions because they have different initial amounts of OH minus in them. And so we can kind of rule that one out already because like clearly it's going to change depending on how much OH minus is already in the solution. But now we have to kind of determine if it's going to be more soluble in a solution that has more OH minus or less OH minus. So what do you think? Will it be one that has like more OH minus in it or less OH minus in it?
More.
So it's actually going to be more soluble in a solution that has less OH minus in it, because if you think of like Le Chatelier's principle, right, and you have like NgOH2 going to Mg plus or Mg2 plus and 2 OH minus. If you have a greater concentration of this, which way is the reaction going to shift if you have more of the OH minus? Which way will it shift?
To the reactant side, right?
Yeah, it'll shift to this side. And this is the solid side. And so it's going to actually dissolve less. And so because of that, the solution that has the lowest pH is going to be is going to have the highest solubility because it's going to have the lowest concentration of OH minus initially. Does that make sense?
Yeah, no, you know what? I made a mistake. I thought you were saying which side needs more like H plus.
Okay.
So yeah, it makes sense.
Okay. Yeah. Does that make sense to you too, Bryce?
Yeah, so the greatest solubility would always be like the greatest number or the small? I think I get confused on that.
Wait, what'd you say? Could you say it again?
When you're trying to find the greatest solubility, it would always be the smallest then, correct? The smallest number?
Yeah, so you'd want like the smallest initial concentration to have like the greatest solubility.
Got it. Okay.
Okay, so this next one was about like acidity, or like solubility in a solution that's acidic versus in pure water. And so for this one, we can start with CaOH2. So this one is kind of the exact same premise that we just talked about, how it's more soluble in like an acidic solution because that basics or like water is going to have a higher concentration of OH minus than like an acidic solution. And so CaCO2 is going to be more soluble in an acidic solution. And then for the rest of these, so for Hg2Br2, that one's going to be more soluble in water because Hg2 is actually, so Br minus, if you remember from like HBr, is just like this is a strong acid. This is just a spectator ion and it would be Br minus. And because of that, it acts as like a weak base. And so, because it's like part of a strong acid, it wouldn't even act as a weak base because it's like so comfortable being, if you remember how we had done before when it was like the like salts, whether it would be neutral or have a pH in it, does it like cause a neutral pH because Br is just like going to be a spectator ion because it's bonded to HBr, which is a strong acid. But the Hg, the mercury, would be part of a because it would be part of a weak base by itself, then it would become a weak acid. And so because it's already like part of a weak acid, if you add it to an acidic solution, it's kind of the common ion effect. And so it'll actually be more soluble in water than it would be in an acidic solution because it acts as a weak acid already. And so the answer for that one is water. For CaCO3, it's like the opposite. So for CaCO3, if you break this apart, CaOH2, which we see up here, is a strong base. And because of that, CaOH2 is a strong base. And because of that, Ca2 plus is just a spectator in a solution. It's not, it doesn't act as a strong, it doesn't act as a weak acid. It just like hangs out, doesn't do anything. It'd be a neutral pH. But CO3 2 minus, if you remember, you might have even had like situations where that literally was your weak base. But because H2CO3 is a weak acid, this also would be a weak base. And because of that, the solution that's acidic is going to dissolve it more than the solution that is just pure water, because this is slightly basic. So that one would be acidic. And then AgI is the same concept as the first one here. So let me clear. It's the same concept as the first one here, because for AgI, you'd have I as part of HI, which is a strong, it's a strong acid. I minus would just act like a spectator, or wouldn't change pH or like do anything, that would just be a neutral ion. But the Ag, if you had AgOH, that's going to be a really weak base. And so that would be, it would serve as, Ag plus is going to serve as like a weak acid in a solution. And so because of that, it's going to be more soluble in the water solution than in the acidic solution. So it would be water. Do you guys have any questions about that one?
Yeah, I do. Can you explain A again? I'm still confused to why it's pure water.
So for Hg2, Br2, okay, so if you had Br, if you were to think that in terms of acids and bases, you'd have HBr. And HBr is a strong acid. So if you remember, like maybe a couple mock exams ago, like maybe like last mock exam a couple weeks ago, or in class, you would talk about like whether or not an ion was going to make, or like whether a salt or an ion that's going to be added would be like an acidic solution, a basic solution, or a neutral solution. This one's just going to be neutral because it's bound to a strong acid. So like it's so comfortable holding on to the negative charge, it's totally fine. And the solution doesn't need a proton at all. And so Br minus is just a spectator, the exact same way that like AgI was a spectator. But Hg, on the other hand, if you had HgOH, it would be a really weak base. And so when it does dissolve and you have Hg plus, it would be a weak acid. And so that would be more soluble in water than it would be in an acidic solution, because it already is an acid. So it's like the common ion effect again. Does that make sense?
Okay, yeah, that makes a little more sense. Thank you.
Okay, so then for the next one we have a solution containing sodium fluoride is mixed with one containing calcium nitrate to form a solution that is 0.015 molar in NaF and 0.010 molar in CaNO3 and ask whether or not a precipitate forms, and you're given your KSP. So first thing to do is write your chemical equation, and so you would write CaF2 goes to calcium 2 plus and to F minus. And so when you write your KSP expression, again, because you have that coefficient in front of the fluorine, you would need to square fluorine in your KSP expression. And so if you remember like a while ago when we had done just like basic equilibrium before acids and bases and stuff, you would calculate your Q to figure out which way the reaction is going to move, would move towards your like towards your reactants or towards your products. And so if you remember from that, you can use Q to see which way it's going to move. And so in this case, you'd have to just calculate your Q based on the concentrations that you were given. So you're given your concentration for NaF and you're given your concentration for calcium. And so you can just put those molarities in, and then you have to make sure you just square the concentration for fluorine, because it's because for CaF2 you have the coefficient in front of it. And so you get a Q value of 2.25 times 10 to the -6. And if you remember, if your Q is greater than your K, if Q is greater than K, you'll have to proceed towards your reactants. And hopefully that makes sense, because if you remember your K expressions, it goes products over reactants. So I'm just put products over, I'm just going to put reactants. Okay, but anyhow, so if you have your products over your reactants, if your Q value is greater than your K value, that means that you would need to be adding more to your denominator in order to make the number smaller. And so if you're adding more to your denominator, you need to be adding a higher concentration to your reactant. And so because of that, when you have a Q that's greater than a K, it means you're going to go towards your reactants. And in this case, towards your reactants would mean that CaF2, which is the only solid, which is the precipitate, will form. Do you have any questions about that one? So the answer was yes, the precipitate forms. Do you have any questions about that one, or does that make sense? Okay, if you aren't sure, but there's a few more like this, so we can go over. This next one is also about whether or not a precipitant will form. And so this one is just kind of like a more complicated version of this one, because you're given volumes and molarities. So you need to go backwards and calculate the new molarities based on when you have a total volume for this. So in the previous one, you're told that it forms a solution that is 0.015 m in this and 0.010 m in that. But here we're mixing two solutions together, so we define their concentrations of like the final solution. And so we can write just like we have, we're making AgCl. We have a KSP for that, and AgCl, because it's just Ag is 1 plus and Cl minus is 1 minus. There's no stoichiometric coefficients, and so it's just Ag plus times Cl minus. But we've defined their concentrations. We can use the molarity that is given to us and the volume that's given to us in order to figure out how many moles there are. And then we can use the total volume of the 175 milliliters and the 145 milliliters in order to get our total volume. So for example, for the Cl minus, we are given that we have a solution that is 0.0055 molar, and we're mixing 175 milliliters of it. So you would do 0.0055 times 0.175 liters, because molarity is moles over liters. And you get 9.6 times 10 to the -4 moles of Cl minus. And then for your total volume, you'd have 175 milliliters of KCl and 145 milliliters of AgNO3. So you would add these two together in order to get your new total volume. So your new total concentration of Cl minus is going to be 3 times 10 to the -3. And it's the exact same process for the moles of Ag plus. So you'd multiply the molarity by the number of you multiply the molarity by the volume. So you have to convert the milliliters into liters, and then you'd multiply, you get your number of moles, and then you divide by the total volume of both solutions. And so your concentration of Ag plus is then 6.8 times 10 to the -4. And so in order to figure out your Q value, just like how we did last time, you would do, if you remember, your Q is just like, your K is just a special case of Q when it's at equilibrium. So your Q is going to be used to see whether or not you're at equilibrium, or if you're going to be shifting more towards the reactants or more towards the products. And so you just multiply these new concentrations that you have. So 6 times 8 times 10 to the negative, or 6.8 times 10 to the negative fourth times 3.0 times 10 to the negative third. And you would get a Q value of 2.0 times 10 to the negative sixth. If you compare this to your, so if you remember before how we would compare our Q values to our K values, in this case, our Q is 2.0 times 10 to the negative sixth. So Q is greater than our K value. And so what that tells us is that a precipitate is going to form because the precipitant is our solid here. If you remember, like the precipitant means that it's a solid forming in a solution. And so in this solution here, we have to do our, like for any kind of a Q value, it would be reactants over products. And so if your K, or if your Q is greater than your K, it means that you need your Q value to get smaller in order to get closer to your K. If you need your Q value to get smaller, that means that your denominator has to increase. And so the concentration of your denominator has to increase, and or that your concentrations of your numerator has to decrease. And the only way for the concentrations of your numerator to decrease is if you shift towards the reactants and form more of the reactants. And so in this case, because Q is greater than K, that means that we're going to shift towards the reactants, towards the AgCl solid, which is the precipitate. So the precipitate will form in this situation. Are there any questions about that?
No, that makes sense actually.
Okay. All right, so for the next one here, we have determine the minimum concentration of NaF needed to cause the precipitation of BaF2 in a solution with 0.035 molar BaNO3 too. And we're given the KSP for this value. And so what we need to do here is to solve for the F concentration that would be necessary for precipitation, and then we can use that to figure out the concentration of NaF that we would need in order to have the F concentration that we need in order for precipitation. So to be more clear about that, we have our KSP value, we have our Ba2 plus value, but what we need to find out is our F minus concentration that would be needed to reach this KSP, and then you would have to use that in order to figure out what your NaF was. So I guess part of the important thing here is determine the minimum concentration needed to cause the precipitation of BaF2. And so what that means is that your K value is right in the center between where a precipitant is going to form. So any more than your K value and a precipitant is going to form. So when it's asking you for the minimum concentration of NaF, or it's asking you like how much would you need of this before you form a precipitant, it's going to be at the K value, because any more than the K value, is going to cause precipitation. And so we're given our K value, we're given our concentration of Ba plus or Ba2 plus, because we have BaNO3 too. We have the concentration of that, which is going to give us Ba2 plus. And so if we're looking at our KSP expression, the one thing to keep in mind here is that we have a coefficient of 2 in front of the F minus. And so we just need to square the F minus in our equation, in our KSP expression here. And so in order to solve for our F minus concentration, we have to divide first by the Ba2 plus concentration, which is this 0.035 molar, and then you would square root it. And so you would get an F minus concentration that you need of 0.0265. In order to convert that to NaF, it's actually pretty simple, because for every 1 mole of, in this case, it's simple, because for every 1 mole of NaF, there's 1 mole of F minus. And so it's going to be the exact same concentration of NaF that you need. So you'd need 0.0265 molar of NaF to cause precipitation. Are there any questions about that one?
How come you use 0.035 again? Like, how does that, like the BaNO3,
So
have the same, I guess, for the BaF2? I guess, I don't know.
So for we use the 0.035 molar, we plug that in for the concentration of Ba2 plus. And the reason for that is BaNO3 is soluble. If you remember, like at the end of last semester, you went over solubility rules of
Yeah.
solutions. This is one of the ones that, like, this is just very soluble because nitrate makes things usually really soluble. And so because for BaNO3 2 is going to end up dissolving into Ba2 plus and then 2NO3 minus, and there's a 1-to-1 molar concentration for Ba2 plus and BaNO3 2, because for every 1 mole of BaNO3, for every 1 mole of BaNO3 2, you're going to get 1 mole of Ba2 plus, and so you can just plug in the concentration of this compound for the Ba2 plus. Does that make sense?
Yeah, that makes sense. So like if it wasn't soluble, would this just not be possible, or like is there something else you're supposed to do?
So if it wasn't, I don't think they would ever, like in this kind of situation, I don't think they would give you anything that would be insoluble, because
Then I don't gotta worry about it.
yeah, I don't think so, because
Alright.
you wouldn't be able to form a new precipitant if you already had, if you're putting something that was insoluble in a solution, it wouldn't be able to dissolve to create a different precipitant. You know what I mean? Like it would just
Yeah.
be powder in a solution.
All right.
Got it. Are there any other questions? That was a good question about it. Does the idea of like the K being the border between where there is and isn't precipitation, so you, when it asks for like minimum concentration, you can just use a K value? Does that make sense? Because that's important for the next part of this too, with the selective precipitation.
Wait, you're saying that it's like the border?
Yeah, so if you remember, like if you had Q greater than K, like how we had just talked about in the
Going to precipitate?
you're going to form a precipitate. But if you have Q is less than K, that means that you're going to create, like you're going to dissolve more of the solution. And so dissolve more of the solute, dissolve more, in this case it would be more of the AgCl if Q was greater than K. But at Q equals K, that means that you're like right at the border between these two values. And so if you were to add in any more of the like F minus in this case to the solution, you would end up creating a precipitant, because then Q would be greater than K if you added any more in. So you can kind of use K as like this frame of reference between when it, like at the minimum concentration to cause a precipitant.
Okay, got you.
Okay. So that's like really important for the next questions that I look at here. I don't know if you guys did this in lecture. Have you guys done selective precipitation? Like these kinds of problems where you have a solution with different compounds in it, and then you can like precipitate one out before you precipitate another one out.
If we have, I do not remember.
Yeah, my study group, when I study group on Tuesday, I don't think you guys have gone over it yet. So I don't know if you're going to go over it. It's still a good practice for like KSPs, but it seems kind of weird to me that you wouldn't have gone over it, but I'm not sure. Like they might just be trying to like decrease the amount of information to go over. So I guess if you were to get a question like this on an exam, at least you'll have seen something like that before, because they're kind of a weird question, I think. The premise of it is that you're given like a solution that has two different ions in it that have different KSP values. And so when you progressively add in an anion, in this case, CO3 to negative, as you progressively add that in, one of them is going to precipitate out first, because you're going to have reached that K value, and then Q is going to be greater than K before you've precipitated out the other one. So you could like precipitate a metal out of seawater, for example. So like, I think that there was a thing where the people would like, would use this for like mining of certain elements out of certain like solutions or something like that, because you could get like, even if you were to get like gold to precipitate out first, you could precipitate that out, you could just collect the gold and separate that from the other cations in the solution. Or you could do it for like filtering water and stuff like that to get those ions out first. So you could like precipitate lead out. So you could collect all that precipitate and just kind of like filter it but have the other cations that are okay for us to drink still in the water. Stuff like that. And so that's what selective precipitation is used for. And so one of the really important things that just figure it out is like to figure out which of the two substances is going to precipitate out first. And so in this situation, you're given the KSP value for FeCO3 at 3.07 times 10 to the negative 11th. And you're also given the KSP for MgCO3. And that one's much larger. It's 6.82 times 10 to the negative 6. And so in order to solve for which one was going to precipitate out first, it's going to be a smaller KSP value. And the reason for that is like, because the precipitate starts to form when Q is greater than K, once Q is greater than K, you're going to have a precipitate. And so the idea behind it is that once you start getting, like whichever one you're able to raise the Q value above the K value first is going to be the one that precipitates out first. So if that K value is smaller, it's going to be easier to get the K value or the Q value above the K like pretty quickly. Does that make sense? Are there any questions about why FeCO3 would precipitate out first because it has a smaller KSP, or does that make sense? Or is it confusing?
That makes sense.
Okay. So that's kind of an important idea for the next question, because it's just telling you like which what is the minimum concentration that's going to trigger the precipitation of the first cation that precipitates out. And so you have to know which one is going to precipitate out first, because you have to use that concentration in that KSP. And so we know it's the iron because it has the smaller KSP value. And so in this case, our KSP is just Fe2 plus times CO3 2 minus, because it's a 1-to-1 ratio, so there's no stoichiometric coefficients. And so we have our KSP value, which we've talked about before in the last one, how that's like the borderline between when there is and isn't precipitation. So when it's asking you for the minimum concentration of K2CO2, it's going to trigger the precipitation. We can use our K value as like that borderline between not having a precipitant and having a precipitant. And so we're given our K value and we're given the concentration of Fe2 plus that's in the solution already. So what we really need to solve for here is this concentration of CO3 2 minus in order to figure out what the minimum concentration of K2CO3 minus, or sorry, K2CO3 is that will trigger the precipitation. And so in this case, all we have to do is divide this KSP value by our 0.022, which is the concentration of our Fe2 plus. And so we're given a CO3 2 negative concentration of 1.40 times 10 to the negative 3rd, or sorry, 10 to the negative 9th molar. And so when we think about that in terms of how much K2CO3 we have to add, there's only 1 mole of CO3 in each in each mole of K2CO3. And so it's the same amount of CO3 2 minus as K2CO3 that have to be added. So the answer to this one would be 1.4 times 10 to the negative 9th. So just do this. Does that make sense? Or do you have any questions about how I did that or anything? It's the same concept as the one that we did earlier.
Yeah, that makes sense.
Okay.
Yeah, I mean,
Okay. So then we have to just do it again. Now it's asking, sorry, I went down too far. Okay, so now it's asking what is the concentration of the cation that's remaining when the precipitation of the other, or when the other cation starts to precipitate out. So I think that this one is like the more confusing out of all 3 of the questions that revolve around this solution. So what it's asking you is like, when we've precipitated out this iron, right? When you precipitate out iron, it's not only the CO3 2 minus that's going to precipitate out, it's also going to be the concentration of, like the concentration of iron is also going to decrease because a precipitant is going to form. And that's like the whole idea behind like the selective precipitation, is that you can get that cation out of the solution. So you could get that gold out, you could get that lead out of the solution. You want that to precipitate out. You want this concentration of aqueous cation to decrease in order to get it as a solid. And so it's really asking you is like, this CO3 2 minus concentration, once you get the other cation to precipitate out, that concentration of your first cation is going to have decreased, because in order to maintain equilibrium and maintain in order to have maintained equilibrium as the CO3 2 minus concentration kept increasing, your cation concentration is going to really decrease a ton. And so there's kind of two steps to this, to solving this problem. The first one is solving what the concentration is of CO3 2 minus is going to cause the precipitation of MgCO3. And the second part is then plugging in that concentration of CO3 2 minus into the KSP expression we had for the FeCO3 in order to determine how much Fe2 plus is remaining. And so this first part of the solution is just, or this first part of the answer is just like how we solved number 13, except instead of using FeCO3, we're using MgCO3. And so again, K is kind of the borderline between Q being greater than K and Q being less than K, and at K, Q equals K. And so when we're at that stage, is like any more than that, if Q is any greater than K, you're going to have you're going to form precipitate, because it's going to go back towards the reactant side. And so you have your K value as 6.82 times 10 to the negative 6 for MgCO3, and you're given the concentration of Mg2 plus just in the problem. So we can solve for the amount of the concentration of CO3 2 minus that would be necessary in order for Mg2 plus to start precipitating out. And so we would just divide that KSP value by our concentration of Mg2 plus in order to get an overall concentration of CO3 2 minus as 4.87 times 10 to the negative 4th molar. But you're not done yet, because what it's asking you is how much of the original cation, in this case iron, is going to be remaining once the MgCO3 precipitates out. So in order to maintain equilibrium, if you have a fixed K value and your CO3 to negative value just increased a ton, because it went from 1.4 times 10 to the negative 9th molar to 4.87 times 10 to the negative 4th molar. So it really increased a lot. And so if you're going to have increased this concentration, in order to keep the same number, the Fe2 plus concentration is going to have to go way down. And so in order to solve for it, we would just have to divide the KSP value of FeCO3 by the concentration of CO3 2 minus that we just solved for in the previous in the previous part of this problem, which is 4.87 times 10 to the negative 4th. And so when you solve for the concentration of Fe2 plus remaining, it's only 6.3 times 10 to the negative 8th molar. So it would be this one. Are there any questions about that?
No.
Yeah, I don't know. I had like a lot of trouble when I was in chem solving for these kinds of things, but I think when you really like break it down, hopefully it makes some sense for why you're doing this.
Yeah, it seems sort of repetitive, actually.
Yeah, I think this whole thing is repetitive, and I think that part of it too is that because you guys have just not gone over a lot of material before your new exam, or like since your last exam, a lot of these questions are just all about KF and KSP.
Gotcha. Yeah.
So this is kind of the transition, I guess, from KSP. The first 14 questions were all about KSP, and now we kind of transition into KF here. And so if you remember, KF is when you're forming those complex ions. And so in this case, we have we're given a solution that has 2.8 times 10 to the negative 3rd molar and an AgNO3, and that's 0.1 molar in sodium cyanide. And so in order to figure out what concentration of Ag plus remains, we're given the KF out to solve for how much Ag plus is going to be remaining after it reaches equilibrium. So this is what you guys did in recitation on I think it was on Tuesday that you did this recitation. And so you have your complex ion here. So your equation for your complex ion will be the silver plus 2 of the cyanides end up yielding this complex ion, which is an AgCN2. And it's all raised to the negative, or it's all like a negative. So it has a negative 1 charge. And so your KF expression is going to, I know our last our KSP expression didn't include our like the molecule because it was a solid, but in KF, these are aqueous, so they get put into your KF expression. And so you're given your KF value and you're given your concentration of Ag NO3, so that gives you your Ag plus concentration, but you have to figure out your concentration of Ag plus. And so if you were to look at like an ice table, because I didn't make an ice table in the answer key, but we can make one. So let me just minimize this. For an ice table here, you'd have your Ag plus your Cn minus would yield AgCN2. Minus. And because it has 2 in it, you'd have to balance your equation and include a 2 in front of the cyanide. And so in order to have an ice table here, you'd have your initial concentrations, your change, and then your equilibrium. And so for the Ag plus, you'd have an initial concentration of 2.8 times 10 to the negative third. For the Cn minus, you have initial concentration of 0.10. And then you don't have any of your complex ion at this point. So now you have to determine which is the limiting reactant. So out of the two of these, is the cyanide or is the Ag plus the limiting reactant?
The cyanide?
So it's 2.8 times 10 to the negative third molar versus 0.1 molar. So which of those is going to be a smaller concentration?
Oh, 2.8 times 10 to the negative 3.
Yeah, so your silver is actually your limiting reactant here. Does that make sense?
I always look at the coefficients first or something.
Oh, yeah. Okay, so your silver is actually your limiting reactant, and so you would subtract, and it's going to be almost to completion here, so almost entirely all of your 2.8 times 10 to the negative third. And you'd have to just consider that for this, because there's a 2 in front of the cyanide, this is a coefficient of 2, you have to do double the amount. So you would do 2 times about 2.8 times 10 to the negative third. And then you would add the 2 times 8 times 10 to the negative third. So this would be minus, then it would be plus 2.8 times 10 to the negative third. And so you know their concentration of AgCN2 is going to be 2.8 times 10 to the negative third. And for this one, it's going to be 0.1 minus 2.8, or sorry, 0.1 minus 2 times 2.8 times 10 to the negative third. And then for this one, you might be like, for the silver, you might be like, okay, it would be 0. And it would be really, really close to 0. It's going to be a really small number, but it can't quite be 0, because if you see our KF expression here, up here, Ag plus is included in it, and it's in the denominator. And so if your concentration actually went all the way to 0, it would reach, your KF value would be infinity, which is like not possible, you know? If your KF did reach infinity, it would just proceed in the reaction in order to get some concentration of Ag plus back to maintain equilibrium. And so that's why at equilibrium, it wouldn't be, when it asks you the concentrations at equilibrium, it wouldn't be that this value actually equaled 0, because there's no way that could equal KF, because KF is not infinity, it's just a large number. And so we're going to put that in as X to figure out how much Ag plus actually remains. And so when you solve for your concentration of Ag plus remaining, you're literally just solving for that X in that concentration. So you remember your Kf was your products over your reactants. So it was AgCN2 minus, which we have a concentration of 2.8 times 10 to the negative third molar for. If you do 0.1 minus 2.8 times 10 to the negative third, 2 times, you'll get 0.0944, and then you have just to multiply, or sorry, you would square this value because it has a coefficient of 2, and then you'll multiply by x. And so to solve for x, we can just do a flop. So you would actually like, you could just, in order to solve for x, instead of like actually like multiplying over this value and dividing over this value, you can just do like a flip. So you would just put Kf in the denominator and x in the numerator, because that's ultimately going to be what happens if you were to like work mathematically backwards in order to solve for like how to undo the expression. And so you'd end up getting x equals 2.8 times 10 to the negative third divided by 0.0944 squared times your Kf value, and your Kf value is 1 times 10 to the negative 21st. So I'm going to clear all of this and go back to the answer key. And so here it is. You have 2.8 times 10 to the negative 3 over 1 times 10 to the 21st, which is your Kf value, times your concentration of Cn minus squared. And so you should get an overall X value of 3.1 times 10 to the negative 27th molar. And this should kind of make sense because you should know this concentration should be like really small, because we had just talked about how it couldn't be 0, but it was going to be almost 0. So in this case, it would be, I think it was 3.1 times 10 to the negative 22nd. Are there any questions about how to do that or how to solve for that?
No, I get that.
Okay. Kelly and Lone, is that good? Do you have any questions about that?
No, I think I'm good.
Okay. So if we go on to the next one here, we're given the KSP of PbCl2, and we're given the Kf of PbOH3, and we have to figure out what the K SP and the Kf values are for, or sorry, to find the equilibrium constant for the reaction of these two together. And I feel like that's the wording of the question that was not super obvious, but the overall expression here that you're supposed to be using these two KSP and Kf values for is that you combine them together into one equation. And so what the whole point of like doing this Kf thing is that when you have Kf, it ends up making a complex that has lead in it. And so your PbCl2 is going to keep dissolving because you're not going to reach equilibrium, because you're not going to have any of the Pb2 plus just floating around in the solution. And so you'd have this equation where you have PbCl2 plus 3OH minus yields PbOH3 minus plus 2Cl minus. And so in this expression here, if you have like your KSP expression is going to be PbCl2, and it would yield Pb2 plus and 2Cl minus. And then your Kf expression for PbOH3 would be PbOH3 oh, sorry, I think that this should actually be a product. So you'd have Pb2 plus 3OH minus yields this PbOH3 minus. And so this is aqueous, this is aqueous, this is aqueous, this is aqueous, and this is aqueous, and then this is solid. And so we'll look at these two expressions, we combine this together because these are both aqueous and they're on opposite sides of the reaction. This is on the reactants, this is on the products. The Pb2 plus is gonna end up canceling out, just like how you did in recitation. I think it was on Tuesday. But everything else is gonna remain. That's what you see in this overall expression here. And so what you're really doing is adding these two equations together. And when you add equations together, you end up having to multiply their k values together. And so in order to solve for the k value of this expression here, you have to multiply the k value of your KSP and the kf value in order to get your new k. And so your new k value would be 9.36 times 10 to the 8. Do you have any questions about that one? So it'd be this. Any questions, or are you guys good on that? Okay. If you're good on it, we'll go forward to the next question is, you're given, you're trying to find the molar solubility for magnesium fluoride in a solution that is 0.25 NaF. And so this kind of goes back, if you remember the calculations, or I don't think it's actual calculation, but the like when we were thinking about acidic versus basic solutions and we're looking at like MgOH2 and how you would solve for that. And Kelly talked about the common ion effect and what that means. This is really the common ion effect in practice, because we're trying to find the concentration, the molar solubility of a solution that already has some NaF in it. And so we have to solve for the solubility of it. And so we have to write the expression first. So we have Mg2 plus 2F minus. And then we'd have, it really would be MgF2 dissolving into those two ions. So MgF2 dissolving into these. And so if we had an ice table here, we have the initial, the change, and equilibrium. And so we can basically ignore MgF2 because it's not going to be put into the equilibrium expression here. But we have to consider these other two, the Mg2 plus and the 2F minus. And so we'd have 2.250 molar of F minus that we'd start off with, and we'd have 0 Mg plus or Mg2 plus. And so we have to figure out how the S value is going to change depending on there already being some F minus in the concentrate or in the solution already. And so we have, if you add S to this, because there's only one of those, you have to subtract 2S from here because we already have some F minus present in the solution. And so you'd end up having S, and you'd have 0.250 minus 2S. And then you'd have your KXP expression is going to be KSP equals Mg2 plus times F minus squared. But because our K value, so if we were to plug these in here, we would end up getting something really complicated because would have 0.250 minus 2S squared. So we'd end up getting the quadratic in order to solve for this. But our K value is really small, it's 10 to the negative 11th. So we can basically just ignore this like minus 2S here. And so when we plug it into our KXP expression, we can do the small k approximation and just ignore that and just do KSP equals 0.250 S. And let me plug in the KSP. So for this one, we'd have our KSP is 5.16 times 10 to the negative 11. And so our S value is going to be 5.16 times 10 to the negative 11 divided by 2.25. And so we get 2.06 times 10 to the negative 10th as your S value here. Oops. So I think that these answer choices are for just the normal molar solubility of a solution. So if you just solve for the normal molar solubility of MgF2, I think that it would be 2.45 times 10 to the negative 4th. But because we have this ion in it, it complicates it. So it's actually not any of the answer choices. And it would be 2.06 times 10 to the negative 10th. Sorry for that one being wrong as well. It's like we like do this and then I check them and then like my supervisor checks them too, but sometimes we just mess up and I guess we just both did the just the normal solubility. But it would be for that one, it would be 2.064 times 10 to the negative 10th for the solubility with the common ion effect factored in. And so for the next one here, we have another like conceptual problem. So we have which compound is more soluble in an acidic solution than in a neutral solution. So if you remember before, we had done the one that was like, is it more soluble in a water solution versus an acidic solution? This is basically the same premise here. And so looking at common ion effect in comparison to whether the solutions are going to make an acidic solution or a basic solution. And so we can start with AGI. AGI is going to have, so in order for something to be more soluble in an acidic solution than in a neutral solution, we're going to want it to have a to be like a weak base, because a weak base would do better in an acidic solution versus a neutral solution in comparison to either two like completely neutral compounds or one that is acidic, because otherwise you're gonna have the common ion effect going in. And so for example, AGI here, I think that might have been even an example in the earlier problem that we did. You'd have Ag plus, which is going to be a weak acid because AgOH is going to be a weak base, and so it will produce the conjugate Ag plus, which is a weak acid. But HI is a strong acid, so if you had I minus, it wouldn't serve as a weak base, it would just be like a spectator ion hanging out in the solution. So this one is going to be more soluble in a neutral solution because it's actually a weak, it would make a weakly acidic solution. And so because of the common ion effect, it'll be more soluble in a neutral solution. So it's not AGI. And then for PBr2, it's a really similar concept. You'd have, if you had this, if you had PbOH2, that's definitely a very weak base because it's not even going to really dissolve. And so it would produce PB2 plus, which would be a weak acid. And so it would create a solution that was weakly acidic. And then Br2 minus is going to come from HBr, or sorry, Br minus from HBr. And HBr produce Br minus, which is just a spectator because HBr is a strong acid. And so this would make a neutral solution, this make an acidic solution, which would overall make an acidic solution. So for the common ion effect, it would be more soluble in a neutral solution than it would be in an acidic solution. So now we can rule out PBr2. Next one is CuCl. And so again, same premise here. If we had CuCl, the two compounds that it would form, if we were to think about it in terms of like bases and their conjugates, if you had CuOH is going to be a weak base. And so it's going to produce Cu plus, which will be its conjugate as a weak acid. But if you had HCl, that's a strong acid, it's going to produce Cl minus, which is going to be a spectator and create a neutral solution. So if this is Cu plus and it's weakly acidic and this is neutral, it's going to create a solution that's weakly acidic. And so because of the common ion effect, it wouldn't be CuCl because that would be more soluble in a neutral solution than it would be in a basic solution, or sorry, than it would be in an acidic solution. And so our last one that must be the answer is BAF2. But if we were to think about that, like the other ones, we'd have BaOH2, which is a weak base. And so, oh no, sorry, BaOH2 is a strong base. And so that would produce Ba2 plus, which would just be a spectator. But the F2 would come from HF, which is a weak acid. And so F minus is going to be a weak base. And a weak base is going to do better as far as solubility in an acidic solution than it would in a neutral solution. And because of that, BAF2 is the only compound that's more soluble in an acidic solution than it would be in a neutral solution. Are there any questions about that one? The answer would be BAF2.
That makes sense.
So then for the last three questions here, we're going into like Gibbs free energy and entropy and stuff. So what you guys have been doing, I think that maybe you guys have just done that on like Thursday and Friday or Wednesday and Friday for lecture. So the first question is, which of these processes are spontaneous? So if you remember, spontaneous means like they're just going to happen, like they're natural processes that happen. You wouldn't like need energy in order to make them happen. And so were there any that immediately jumped out as to you as like being a spontaneous like process that just happens in nature? You don't need to put energy into it in order for it to occur?
The first one.
Yes, the first one is definitely spontaneous. Natural gas just combusts. I'm gonna close the chat. So like natural gas is automatically going to combust because it's like entropically unfavorable. So if you look up the combustion of natural gas, you'd have CH4 go plus OH2 going to CO2 plus H2O plus CO plus O2. And so you can see there's way more molecules of gas in the product side than there is in the reactant side. So there's way more entropy when it actually is combusting versus when it's not combusting. And so you can also just think of that in terms of like natural gas will combust if it's like not stored properly, if it's exposed to the atmosphere. And so that's why you'd have like that process occurs spontaneously. You don't have to put any energy into it, just happens. Is there another one of these that you would just think like that just like happens automatically in nature? You don't have to add any energy into it before, like that process just happens by itself. There's one other that just happens naturally.
The second one?
Yeah, exactly. If you have a hot drink out, it's going to cool to room temperature, and that's just going to happen naturally. It doesn't have to, you don't have to have any external energy put into the system in order for that to occur. This last one, sorry, I flipped that, but it should not be selected. This last one, for example, like you have to, it's literally describing drawing energy from the surface in order to power a ship. You have to be getting external energy, which is going to take energy in order to power a ship. And then same with the extraction of iron metal from iron ore. It's not a natural process. Otherwise, you wouldn't have like iron ore existing on Earth. You would only have iron metal like deposits. So it doesn't happen naturally. We have to put energy into it. I think we have to heat it and get that iron and metal out separately from the ore. So then the only two processes that are actually spontaneous are the combustion of natural gas and then the drink cooling to to room temperature. Does that make sense? Are there any questions about those?
That makes sense.
Okay, so for the next one, we have just to figure out the delta S of the system for each chemical equation. So, and when we're given equations like this, do you guys remember how we determine the sign of delta S?
Based upon if it's, oh wait, no, I might have forgot. I think it's if it's spontaneous or not.
So it's like the delta S is going to like help inform us on whether or not an expression is spontaneous. But like when it gives us chemical equations, the one way for us to tell if it's going to be entropically favorable or if it's going to be a positive or negative entropy is going to be the number of moles on each side, because the more entropy that there is, the more like moles of gas there would be, because gas is like so has so much more energy and can disperse so much and has so much more disorder and randomness than a solid does. A solid is like very ordered, very close together. The same kind of concept is like when you have, if you've done it in lecture so far, when you consider like an aqueous solution being more entropically, like having more entropy than a solution that's just like a solid, because that when they're aqueous, there's a phase change there, they're able to move around. And so that's what we're looking for here is like in terms of which side has more moles of gas, because it'll have more disorder for each like mole of gas. And so, for example, for the first one here, we have 2 moles of a solid yields 2 moles of a solid plus 3 moles of a gas. So is there more entropy on the left side of the equation or on the right side? On the reaction side or on the product? Is there more entropy?
The right side?
Yeah, exactly. It's on the product side, because we have these 3 moles of gas here. So like before we just had 2 moles of a solid here, but now on the product side we have 2 moles of a solid and 3 moles of a gas. And so if there's more entropy on the product side, it's going to be a positive delta S, because the change in entropy is greater. It's a positive because it's greater on the products than it is in the reactants. For this one though, we have NaS plus 1/2 Cl2 yields NaCl. Is the reactant side or the product side going to have more entropy for B?
Reactant.
Left side.
Yeah, exactly. Both of you are totally right. It's this reactant side here because we have 1/2 mole of gas here. And if you even think about it in terms of like you have a mole of a solid and a mole of a gas, as opposed to just a mole of a solid and 1/2 mole of a gas, as opposed to just 1 mole of solid on this side. And so because of that, it's actually negative, because there's more on the reaction side than there is on the product side. So delta S is going to decrease in entropy. And then finally, for this last one here, everything is gas here, but we've changed the number of moles of gas on the sides. And so this side has 1 mole of N2 and 3 moles of H2, whereas this side has 2 moles of NH3. And so which side is going to have more entropy, the left side or the right side?
Left side.
Yeah, exactly. And so just like how it was negative when the reactant side has more than the product side, it's going to be just like that for C. So yeah, so the entropy will be greater on the reactant side, which is going to cause it to be a negative delta S. And then finally, you have to fill out this chart for if things were look for what would happen. And so for this one here, you have to refer, I'm not sure if you guys have learned yet in lecture, I think potentially you have. There's the delta G equals delta H minus T delta S. Do you remember this equation? I think you should have learned it by now. Do you guys remember that? Okay.
Yeah.
Okay, cool. I wasn't sure because we go over the meetings on like Wednesdays, so I'm not always sure how far you guys get in lecture. Okay, so you have delta G equals delta H minus delta T delta S. And so for this first one here, we're given, so I guess it's also important. In order for a reaction to be spontaneous, is delta G positive, negative, or 0?
Negative, right?
Yeah, it's negative. And so for this one, we are told that delta G is always negative. And so that already tells you that even at high temperatures, it's going to be spontaneous. But you're going to think about it in terms of this equation here, and not think about it in terms of, and if you want to pretend you don't have this delta G column here yet, if you had a negative delta H and you're going to subtract a temperature minus or temperature times delta S, no matter what temperature you're at, because your temperature times your delta S is always going to yield a positive number, and you're subtracting that from a negative number, you're always going to get a negative delta G, which means that at any temperature, it's going to be spontaneous. Does this row make sense? Are there any questions about that?
That makes sense.
Okay.
Yeah.
Okay. So now we have a little bit harder. We're given our delta H is negative and our delta S is negative. And so our delta G is actually temperature dependent. And so is the solution going to be, or not solution, is the process going to be spontaneous at a high temperature or at a low temperature? This is negative, and then we'll be subtracting another negative. So would you want this number to be big, or would you want it to be small?
Big.
So because you're subtracting it, it's actually gonna go, so if you have a negative delta H, so if you have negative H, and then you'd have plus this here.
Oh, my bad. No, yeah.
Actually want it to be a small, right? Because if it's small, then you're not like changing it. You're not going to make this much less negative, or you wouldn't make it positive. So your overall delta G could still be negative. And so because of that, it's only spontaneous at low temperatures. And so it'd be spontaneous at low temperatures, but non-spontaneous at high temperatures. Because if you got like this T times delta S to be too like large, a really large negative number, if you subtract a large negative, it's gonna be like you add a lot of positive. If it cancels out the negativity of the delta H, your delta G is gonna be positive and it would be non-spontaneous. Okay, so now we're given delta H is positive and delta S is positive. And so we have this being positive and this being positive. So is delta G going to be positive, negative, or temperature dependent?
I had no idea.
So, okay, so you'll have delta H is positive, right? So it would be like positive, let's say in this case, it's positive 2. If you had delta S, let's say, okay, so let's say that we have, let's actually say that we have delta H is a positive number because it's equal to 10 joules. Minus, we have delta S is positive as well. Let's say it's equal to 2 joules. And so if we had a temperature of 5 Kelvin, or let's say 3 Kelvin, so we don't go to 0. If we have a temperature of 3 Kelvin, then it would be 10 minus 6 equals 4. And so delta G would be positive. But if we had 10 minus 3, or sorry, 10 minus, and then if our temperature was like 20 degrees Kelvin, we'd have 10 times 20 times 2 joules for the S. And so then it would be 10 minus 40, which is going to give us negative 30, and this reaction would be spontaneous. So does that help a little bit? Would it be positive, negative, or temperature dependent?
Temperature dependent.
Exactly. Does that make sense, or does that not make sense?
I mean, yeah, it makes sense.
Okay. How do you guys feel about it, Lone and Kelly?
Yeah, that makes sense.
Okay. And so we're already given that at high temperatures is spontaneous, but at really low temperatures, would it be spontaneous or non-spontaneous?
Non-spontaneous?
Exactly, yeah, because For example, like how I did this example here when we had H equal spontaneous. Okay, when we had 10 equal delta H and 2 equal delta S, at a low temperature, it was non-spontaneous. It was because it gave us a positive number. And then at a higher temperature, it was actually spontaneous because this value, this T times S, was large enough to cancel out the delta H and bring it down to a negative number. Okay, so we're given one last row to fill out. And we are given that at all temperatures is non-spontaneous. We aren't given the sign for delta G, and we aren't given the sign for H yet. So it's probably easiest to figure out the sign of delta G first here. So if it's always non-spontaneous, what's the sign of delta G going to be?
Positive.
Exactly, because if it's negative, it's spontaneous. If it's positive, it's not spontaneous. And so if delta G is always positive, and this equation is positive, or if this equation is delta G equals delta H minus delta TS. So if we have delta G is positive, so we have a positive number equals delta H, so a question mark, because trying to figure out the sign of that is, and then it would be minus a negative, which is going to give us, so minus a negative, which is going to give us a plus, so it would be plus equals blank plus a number. So then what would this have to be in order to make sure that it was always going to be another positive here? If you're adding a positive number, you want to make sure it's always positive. What would it have to be?
Positive.
Exactly. So that would be okay, so I'm just going to send that out. So that would be positive. Do you guys have any questions about anything? Do you want to go over anything again? Does everything make sense? How are you guys feeling?
That definitely going over it makes a little bit more sense.
Okay. Are there any questions that anyone wants to go over again, or any other topics that you guys would want to go over? I know that right now it's like you guys haven't learned that much since the last exam. So I know the mock exam was a lot of the same types of questions with KSP and KF, but hopefully it makes a bit more sense now. And you got some practice and you're feeling good about that. Okay, I'm just gonna, if you hear a screenshot noise, I'm just gonna screenshot for attendance. If you have any questions about anything that's like the mock exam or the pre-mock exam, or if you have any questions about anything else in Chem right now or about any of these questions, feel free to hang around. But if you don't have to, we went through the whole thing, so you're free to go.
All right. Thank you for your time.
Yeah, of course.
All right. Have a good one.
You too.
Bye.
Thank you. Have a good day.
You too. Do you have any questions, Lone, or anything?